So welcome to everyone for the part 2 of air standard cycle. In this air standard cycle part 2 video, we are going to discuss about diesel cycle. Okay. In diesel cycle, the another name is compression ignition engines. We are using diesel cycle. Okay. So now this diesel cycle is proposed by Rudolf Diesel in the year of 1892 he proposed. Okay. Whereas in this diesel cycle, the air is the only medium which enter into the cylinder, okay, where the combustion during that end of the compression stroke, where you can inject your diesel so that automatically the combustion will takes place, right. So that much of temperature you compressed your air inside the cylinder, right. Okay. Now we move on to the cycle. Okay. In this diesel cycle, this is your PV diagram and then TS diagram of your diesel cycle. So the first thing is 1 to 2, again it is the compression process, whereas 2 to 3 it is the constant pressure process, 3 to 4 again it is that isentropic expansion, and then 4 to 1 again it is the constant volume process. Okay. So already in that previous video also we discussed about where the heat is, the work is there, where the heat is there, everything we discussed in the previous video. Okay. In this video, in this lecture, we discussed that, look into that, V1 is equal to V4, right, because the heat rejection will takes place at constant volume process. Okay. The 1 to 2 is the isentropic compression, again the isentropic compression other name is reversible adiabatic, right. Okay. So whereas in the reversible adiabatic you just compress your air and then heat is supplied at what is that, constant pressure process. In that previous Otto cycle where heat is added at constant volume process, whereas in the diesel cycle the heat is added at constant pressure process. Okay. So then 3 to 4 it is an expansion, that is isentropic expansion or reversible adiabatic expansion process. Again 4 to 1 it is constant volume process. Okay. See, in that previous video itself I said that irrespective of any cycle like auto, diesel or dual cycle, your heat rejection will takes place at constant volume process. Okay. Then few more things you just remember in this. In Otto cycle, that is V1 is equal to V4 as well as V2 equal to what is that, V3. But in that diesel cycle it is not like that. You must be very careful on it, right. That is V1 is equal to V4. See here this is your V2. Okay, this is your V2. V2 is the, already we discussed that V2 is the clearance volume. Okay, V2 is the clearance volume. Then V3 which is somewhere which is more than the V2, right. Okay, that is not a clearance volume, which is, this is your clearance volume, okay, VC, okay, this is your stroke volume, that is Vs is the stroke volume, or else we can call it as a swept volume. Then here pressure, this is your pressure P1, 0.1 the P1, here you just remember that P2 equal to what is that, P3. Okay, because the pressure remains constant in your heat addition process. Okay. Then similar to that, this is in TS drawing it is opposite to this PV drawing. Okay. So whereas here it is the curve, then it will be in that straight line. Okay, like already we discussed in that in the previous video also. Okay. So here the process 1 to 2 is the isentropic compression. See, already we said that this is that isentropic compression. There is no heat losses will take its place, so that isentropic there is no heat transfer will take its place within your system and surrounding, so that entropy remains constant, that is S1 is equal to S2. Then 2 to 3 it is that heat constant pressure process 2 to 3, and then 3 to 4 again it is the expansion process, again it is the reversible adiabatic, so that S3 is equal to S4, right. And then 4 to 1 again it is the expansion process, again it is the curve like this 4 to 1. Okay. So this is a PV diagram. First, just for reference, I just drawn over here, right? Okay. See, the heat is supplied, that is QS is equal to what is that? MCP, what is that? T3 minus T2, right? See, why I am putting over CP is, here the heat is supplied in the constant pressure process. Okay, between the 2 to 3, it is the constant pressure process. That is why I just put CP over here, right? See, the temperature is, again, the peak temperature in this cycle is 3 is the peak temperature cycle. Okay, because after the heat addition, the temperature reaches the maximum, right? So that is why I just put this, T3 is the maximum temperature minus minimum temperature, T3 minus T2, right? Okay. Then heat rejection is taken place in the constant volume process, whereas in the constant volume process, that is MCV T4 minus T1. This is the heat rejection. Okay. Here I just put the CV. The reason behind is, what is that? Here the heat rejection will take place at constant volume process, that is MCV T4 minus T1, right? So again, based on that second law of thermodynamics, if there is an engine, whatever the heat that you can supply, partial amount of heat is only converted as work, and then remaining amount of heat is entered into the rejection, right? So heat supplied is equal to that, W plus heat rejected. Okay. So if you want work done, you can write it as heat supplied minus heat rejected, right? So efficiency equal to that, output by input. The input which is supplied as, what is that? Heat supplied. Then what is the output? This is your output, right? Work is the output. So that we can write the heat supplied minus heat rejected. Okay. So we have a formula, that heat supplied minus heat rejected formula. So MCP into T3 minus T2 minus of heat rejection is MCV T4 minus T1 divided by heat supplied is MCP T3 minus T2, right? Now you can simplify this. Okay, so you can take it this as a one direction. Okay, you just take it this as a one thing, and then this as one thing, right? Okay, so you can cancel, neglect it on the both the sides. Okay, if you simplify this, 1 minus, see here the mass gets cancelled, right? Okay, here you have CV by CP. Okay, so we all know that, right? CP by CV equal to what is that? CP by CV equal to only you have gamma, right? But here we have CV by CP, so there is 1 minus gamma into T4 minus T1 divided by T3 minus T2, that you will get it, right? Okay. Okay. So again, you just look into this. You have if you know all the temperatures in the cycle, so the temperature T1, T2, T3, T4, if you know all the temperatures in the cycle only, you can able to find the thermal efficiency. Okay. If you know all the temperatures only, you can able to find the thermal efficiency, right? Okay. So we have to look into other way to find the thermal efficiency without knowing the temperature. Okay. Now we will discuss that. Yeah. See, whatever that we discussed over in the previous slide, the same which is on here. Okay. So already in the Otto cycle we discussed about a compression ratio. R is equal to what is that? Total volume divided by clearance volume, right? So total volume here the same, that is V1 divided by V2, that is what is that? V1 is the total volume, V2 is the clearance volume. Cutoff ratio. The cutoff ratio, which is denoted as rho, the formula for this cutoff ratio is V3 by V2. See, V3 is nothing but, what is that V3? V3 is nothing but only the heat is added up, what is the volume, that is we can call it as V3. Then what is V2? V2 is compression, clearance volume. At the end of the compression, whatever that volume which you left it over in that cylinder, that is the clearance volume, that is we can call it as V2, right? Okay. So cutoff ratio, which is defined as rho, is equal to V3 by V2. V3 is nothing but the volume after combustion divided by the volume after compression. We can call it as cutoff ratio. Okay. Now we move on to that process. In the process 1 to 2, okay, the process 1 to 2 is nothing but what is that? Isentropic compression process. Okay, if it isentropic compression process, we can write it your temperature volume relation. You have to write your temperature volume relation by T2 by T1 is equal to V1 by V2 whole to the power of gamma minus 1. Okay, see, already we discussed that T1 is nothing but what is that? The temperature at atmospheric. Okay, then P1 is the pressure at atmospheric, right? So we all know that, right? Okay, so the temperature atmospheric by default we know that. Okay, we can write it this as T2 is equal to T1, then V1 by V2 is nothing but what? R. R is nothing but the compression ratio. T2 is equal to T1 into R whole to the power of gamma minus 1. You can keep it this as in process 1 to 2. The same way, the process 2 to 3, process 2 to 3, process 2 to 3, whereas in the process 2 to 3 is the constant pressure process, right? You can add at the heat over here. Okay, you just supply the heat over here. See, in this constant pressure process, you should not use the relations. Okay, like temperature volume or pressure temperature, you should not use that temperature relationship. Okay, so that instead of that, see, by we know that in the thermodynamics we might studied this P2 V2 by T2 is equal to P3 V3 by T3. Okay, see, here it is a constant pressure process, so you just simply neglect the pressure process. Okay, what is the remaining thing? That is V2 by T2 is equal to V3 by T3. Okay, so I just simply bring this T3 in this side and then V2 in this side. Okay, so T3 by T2 is equal to V3 by V2. Then we know that what is the V3 by V2? V3 by V2 is nothing but it is a rho. Okay, that is cutoff ratio. So T3 by T2 is equal to T3 by T2 is equal to rho. See, already we know the T2, right? T2 is nothing but what is that? T1 into R to the power of gamma minus 1. So we can rewrite this as T3 is equal to T2 into rho, that is equal to T2 into, instead of this T2 you can write it as T1 into R to the power of gamma minus 1 into rho. Okay, so this is the equation for T3. This is the equation for T3. Okay, this is the equation for T3 is equal to rho into R power gamma minus 1 into T1. This is the equation for T3. Okay, now we got a T2 as well as T3. Now we have remaining only one thing, that is T4. The process 3 to 4, again it is the isentropic process, where in this isentropic process again it is a reversible adiabatic and an isentropic process, then you can use the temperature volume relation, right? So for this temperature volume relation, that is T4 divided by T3 is equal to V3 divided by V4 whole to the power of gamma minus 1. Okay, so already we know that V1 is equal to V4. Okay, so if it is V1 is equal to V4, we can write it as V3 by V1 whole to the power of gamma minus 1. So we can write it like this. So V3 by V1 into whole to the power gamma minus 1, right? So we don't have any ratios like V3 by V1. So if we don't have any what is that ratio like V3 by V1, so we can rewrite this like this: V3 by V1 into V2 by V2. See, it will not change any values in this ratio, right? Okay, so we can write it as V3 by V1 into V2 by V2. Okay, so on numerator and then denominator both the sides you can multiply with V2, right? I just rewrite this V3 by V2 into V2 by V1 whole to the power of gamma minus 1. Okay, so we know that V3 by rho is equal to what is that? V3 by V2 is the rho, R is equal to V1 by V2. Okay, so but we got here V2 by V1, right? But R is V1 by V2, right? So we can rewrite this as rho into 1 by R whole to the power of gamma minus 1. So we can rewrite rho by R whole to the power of gamma minus 1. Okay, fine. We can write it as rho by R whole to the power of gamma minus 1. So T4 by T3 is equal to rho by R whole to the power of gamma minus 1. Okay, so I just rewrite this as T3 is equal to, T4 is equal to T3 into rho by r whole to the power of gamma minus 1. Now what is T3? In this T3, in your previous slide we discussed that T3 is equal to rho into r power gamma minus 1 into T1 that we discussed, right? Okay. So now you can, instead of this T3 you can substitute this. Okay. Instead of this T3 you can substitute this. Instead of this T3 you can substitute this, and then you can get to this equation, right? Okay. You can get this equation, that is rho into r power gamma minus 1 into T1, right? Okay. See, even if you want to further simplify this, that is rho power gamma minus 1 divided by r power gamma minus 1 into rho into r power gamma minus 1 into T1. This gets cancelled. Here you can write it as rho power gamma into rho power minus 1 into rho. So this rho power minus 1 rho gets cancelled, right? Is rho power minus 1 is nothing but what is that? 1 divided by rho is, we can write it as rho power minus 1. Okay, so it is on numerator and denominator cancel. So the left thing is what is that? Rho power gamma into T1. Okay, so that is why they written over here the T4 is equal to what is that? Rho power gamma into T1 is the T4, right? Okay, now we got all the temperatures like T2, T3 and then T4. Okay, but we didn't find anything on T1. Already said that T1 is nothing but what is that? It is the temperature, inlet temperature, right? Inlet temperature we all know that, so we don't want to find anything on the inlet temperature. So this is the temperature relation. In the earlier we discussed that 1 minus T4 minus T1 divided by gamma into T3 minus T2, right? Okay. See, whatever the temperature that we find, whatever the temperature relations that we find, you can simply substitute in this equation and then you will got this, right? 1 minus rho power gamma minus 1 into T1 minus of T1, you will get it, right? Okay. So I just rewrite this. Okay, I just write over here, right? That is 1 minus T4 that we found that is rho power gamma into T1 minus of T1 divided by, what is that? T3, again the 1 by gamma is there, so that we can put gamma. Okay, then T3 is nothing but what? Rho into r power gamma minus 1 into T1 minus of, what is the T2? T2 is nothing but what is that? T1 into r power gamma minus 1. Okay, so this is the equation that we found already. Okay, so the common thing, what all which is common thing which is present in this equation, you can bring it out, right? Here the T1 is the common, right? So that 1 minus T1 into rho power gamma minus 1 divided by, here also the T1 is the common on both the sides, then r to the power of gamma minus 1 is the common, right? So gamma into r to the power of gamma minus 1 into T1 into rho minus 1, you will get like this, right? Okay, so this T1 gets cancelled. Okay, the remaining thing is what is that? 1 minus 1 divided by gamma into r to the power of gamma minus 1, okay, into rho power gamma minus 1 divided by rho minus 1. Okay, so this is what you can finally get this equation, right, based on that diesel cycle. Okay, yeah, this is the final equation, that is 1 minus 1 divided by r power gamma minus 1. See, simple, in this equation the gamma you can multiply inside, right, nothing wrong in it. So rho power gamma minus 1 divided by gamma minus 1, right? Okay, see, with refer the same equation, air standard efficiency cycle equation with Otto cycle. Here for the diesel, this equation, have you remember this equation, that is 1 minus 1 divided by r power gamma minus 1, the same equation that we saw in the previous video lecture and Otto cycle, right? So again in this diesel cycle the efficiency is depends upon what is that? Two things. One is compression ratio, another one is what is that? Cutoff ratio. See, if it is cutoff ratio, this is rho, right? If it is compression ratio R, right? If R increases, what happen in the diesel petrol cycle, that is Otto cycle? If you increasing the R, then diesel cycle efficiency is also increased. Okay. If you increasing, what happened that if you increasing the cutoff ratio? If increasing the cutoff ratio, what happen? Your diesel cycle efficiency gets decreases. Okay, so you'll just see the graph. You just look into this graph. What happened that the effect of cutoff ratio and then compression ratio on thermal efficiency of diesel cycle. If you increase the compression ratio or the efficiency gets increases. If you increases the cutoff ratio, what happen? You just look into this 1, 2, 3, 4. If you increasing the cutoff ratio, the efficiency gets dropped. Okay, see, one thing that you can remember, the cutoff ratio remains unity. What happened? If it is one unity, then this become 1, then this become 1. Okay, so what happened? Then it both are identical. Okay, even if it is a petrol engine or diesel engine, both are identical when your cutoff ratio is equal to 1. Okay, so you just look in, simply apply this. If it is if you apply that rho equal to 1, 2, 3, 4, what happen your diesel efficiency? If you increasing that compression ratio like 12, 14, 15, 16 or 18 or 20, like that, you can apply your compression ratio, then you can find that what happened in a diesel, right? So from this graph, it shows that if you increasing the compression ratio from 12 to 20 or 22, then it is keep on increasing your efficiency, thermal efficiency. If you increasing the cutoff ratio, so what happened, your diesel cycle thermal efficiency gets dropped. Okay, that you can remember it. That's all for the diesel cycle derivation. I just thank everyone for patient listening. With this, I just wind up this session. Thanks for your patient listening.